So your TA Indiana is just chilling down here today because kinematic coefficients aren't really anything new. Kinematic coefficients are just a different way to express an answer that you're going to solve using an existing method that you already know. And you can use any method that you want. Instantaneous centers of zero velocity, velocity polygons, loop closure method. And that's the method, right? The complex algebra loop closure method. It's a method that basically every student uses for problems, kind of in my experience. But a kinematic coefficient is just a different way to express your answer. Instead of solving for a single value for velocity or angular velocity, you're going to solve for velocity as a function of the input. So your kinematic coefficient is a ratio of output versus input. And this is extremely useful when you have a system where the input speed might be changing. That way, if the input speed changes, you don't have to redo all of the work to get the different answer for velocity of the output. You just multiply by this factor and you automatically get your new answer. So we're going to walk through this example problem where we're going to be solving for the first order kinematic coefficients for links 4 and 5, and then use those to find the angular velocity of link 4 and the velocity of link 5. And link 5 is that slider block at B that's moving up or down. Link 4 is the big pointer, right, that's rotating in a circle. The input for this system is link 2, the crank that's over on the right-hand side. And I'm going to use the method that most students use, which is the complex algebra loop closure method. And right on cue, your TA Indiana gets to work back on his hamster wheel, just like your brain is going to have to start actually spinning here as we write the loop closure equation. And so for starting off for link 4, I'm going to draw my loop using this blue triangle, except technically speaking, I'm not going to draw a loop. I'm actually going to say that the path from O4 to A, just this first diagonal, is equal to a different path to that same point, which is going to be horizontally across the bottom and then up through link 2. If you wanted to write this just as a complete path, just a triangle that goes back to the beginning, you could subtract those right-hand terms over to the left-hand side, but it works just as well to have two different paths to the same ending point. That's still loop closure method. So we've got the length O4A times cosine theta 4 on one side, and then L1, which is the distance I'm calling this base here, plus LO2A, which is the length of the crank, times cosine theta 2. If I write the y direction equation, it's going to be basically the same, just replacing sines for cosines. And instead of L1, it will be 0, because L1 is purely horizontal. It doesn't go up and down at all. So when I take the derivative of my x direction equation with respect to theta 2, I've got my LO4A and cosine theta 4 multiplied by each other, so they both are changing with respect to time. Now link O2A is a constant 10, so that's not going to be an issue, but length O4A is changing because of the slider at A is going to change the length of that portion of the link. So I have to use the product rule on the left-hand side. So product rule is going to be 1 times the derivative of the other, and then the other times the derivative of the first one. So LO4A times derivative of cosine theta 4, which will be negative sine theta 4 times theta 4 prime. And you're used to writing theta 4 dot here when you're doing a time derivative, but it's theta 4 prime when you're doing the derivative with respect to theta 2. So then finish the product rule. We've got the second term, so cosine theta 4 times derivative of the first one, which is just LO4A prime. Right-hand side, the derivative of L1 is 0 because that term is not changing. And derivative of 10 cosine theta 2 will be 10 negative sine theta 2. All right, and now I want to take a real brief aside for a moment and talk about derivatives. So using the complex algebra method, you're probably used to taking a time derivative as the next step. And when you take, say, the time derivative of an angle that is changing, you get, because of the chain rule, an extra term kind of pops off to the side, like a theta dot term. The sort of weird, unique type of thing that's happening here with kinematic coefficients is instead of taking a time derivative, we're going to be taking a derivative with respect to the input angle. So the derivative will be with respect to theta 2. And that's going to seem really weird. As engineers, we almost always take time derivatives because we're interested in how things change in time. That's what velocity is change of position in time. But a kinematic coefficient is a ratio of output versus input. So we need the derivative of the output with respect to the input. So here I'm going to write down just some definitions here first. So omega 4 is equal to theta dot 4, right? I'm just changing the term to give a dot here. And omega 2 is theta dot 2. And we can also rewrite, say, theta dot 4 as d theta 4 over dt. Again, to show that this dot term means time derivative. And same thing for theta dot 2, d theta 2 over dt. Now, if I divide these two terms, theta 4 dot divided by theta 2 dot, that's d theta 4 over dt, divided by d theta 2 over dt, you can kind of cancel out the dt's, and you can show essentially that the derivative of theta 4 with respect to theta 2, which I'm going to call theta 4 prime, right? Not a dot. We use dot for time derivatives. We use prime for derivative with respect to some other axis, like position. So theta 4 prime is equal to theta 4 dot divided by theta 2 dot. Or theta 4 prime is the ratio of the angular velocity of length 4 divided by angular velocity of length 2. This will probably make a lot more sense once you actually see how it fits into this complex algebra solution. Do the same thing for y. We're going to take the derivative of y with respect to theta 2. So length O4a times derivative of sine theta 4, which is cosine theta 4 prime. Now we take sine theta 4 times the derivative of LO4a, which is LO4a prime. And then the right-hand side, 0 plus 10 cosine theta 2. The theta 2 term doesn't need any extra thing because it's not a function of theta 2, it is theta 2, right? The derivative of theta 2 with respect to theta 2 is just 1. And I didn't actually define this LO4a prime yet, right? This is the derivative of LO4a with respect to theta 2, which is essentially going to be the speed of length 3, right? It's the speed of length 3 along length 4. So length 3 will actually be sort of moving in normal tangential components, right? It's both sort of rotating in a circle and it's sliding along the length. This LO4a is only the speed along length 4. Of course, then with respect to the angular velocity of length 2. And I'm not actually going to care what this term is. I'm only actually going to be interested in O4 prime. We move forward in the same way as you're used to for these type of problem. You just put this into matrix form so you can solve it really easily in your calculator. So the two variables being solved for, O4 prime and LO4a prime, and then gather all of the coefficients together on one side, and then all of the independent numerical terms over on the other side. We look at the picture, and fortunately, actually, all of these values are known, right? Theta 2 is given 150 degrees. We can see theta 4 by inspection is going to be 30 degrees. And again, because of this, it's just an isosceles triangle. The length of O4a is also going to be 10. So a little bit of calculator work. O4 prime is negative 0.5, and the units for that are radians per radian, right? This is the angle of the output over the angle of the input. And LAO4 prime is negative 8.66 inches per radian, because again, this is a distance, right? It's measuring how long it's moving, how far, so inches per radian, right? Because it's position divided by angle. So these terms, O4 prime and LAO4 prime, these are the kinematic coefficients, the first order kinematic coefficients. And we can then directly use these to find velocities. So by definition, the angular velocity of link 4, theta 4 prime, is the angular velocity of link 4 divided by angular velocity of link 2. So I can rearrange that to solve for the angular velocity of link 4, 2.5 radians per second counterclockwise. And that'll be counterclockwise because omega 2 is a negative 5 and theta 2 is measured counterclockwise. So then -5 means it's moving clockwise. So omega 4 will be in the opposite direction. UTA Indiana moved over to his napping spot because he thought we were done with this problem. But of course, you're going to realize we were actually asked to solve for two things. We wanted to find velocity of link 5, the slider that's moving vertically. So we actually got to do this one more time just to show you how to find a linear velocity term instead of an angular velocity. It's basically going to be exactly the same, but let's go through it one more time anyway for good practice. So looking back at the initial drawing, the loop closure method, I'm going to draw this green triangle where I'm going to go from 0,4 diagonally up to point B. And then separately, I'm going to draw a triangle over to the left and then up x5 and y5. And I'm going to say, instead of drawing like one path that all adds up to 0, again, I'm just going two different paths that end up to the same location. So those two paths have to equal each other. So in the x direction, LBO4 times cosine theta 4, right? That's the x component of the diagonal link, is equal to x5. Just the horizontal distance plus 0 because the vertical line is not a horizontal line. And then in the y direction, LBO4 sine theta 4 is the vertical component of the diagonal, equals 0 plus y5. Again, 0 because the x direction term is not a vertical term. Same process as before. We're going to take a derivative, but again, not a time derivative. This is a derivative with respect to theta 2. So on the left-hand side of the x equation, we've got a product rule because LBO4 is going to change in time just like the angle changes. Because even though B is moving purely vertical, it's within a slot. So it will actually get kind of the link itself will get longer. So LBO4 times the derivative of cosine theta 4, which is negative sine theta 4, times theta 4 prime because of the chain rule. And again, prime, not dot, because it's a derivative with respect to theta 2, not a time derivative. Okay, finish the product rule. Cosine theta 4 times the derivative of LBO4, which is LBO4 prime. Right-hand side equals 0 because x5 is a constant. Since this slider is moving purely vertical, x5 is not going to change, so its derivative is 0 for any angle. Derivative for the y direction equation with respect to theta 2. Again, product rule on the left side, LBO4. Derivative of sine theta 4 is cosine theta 4 times theta 4 prime. Plus sine theta 4, derivative of LBO4, which is LBO4 prime. And then the right-hand side, 0 plus y5 prime, because even though the horizontal distance is not changing, the vertical distance is changing. So as it rotates, that length, that height will change. And now at first, this seems like a bit of a problem because I have 3 of these prime terms and I only have 2 equations. But remember, this is the second half of the problem. We already did a first half of the problem, which means we already solved for theta 4 prime. So we only have 2 unknowns. And we've got even better news is that if you look at the x direction equation, there's only 2 of the prime terms in that one. The theta 4 prime that we already know and LBO4 prime, which means we can actually find LBO4 prime in just one equation. We don't have to do matrices. So plug in the known length of 15, the 30-degree angle, the negative 0.5 that was known for theta 4 prime that we already found. Again, cosine 30, LBO4 prime is the last unknown to solve for. Negative 4.33 inches per radian. Again, it's a length divided by an angle. The radians is from theta 2, the input. The inches is the length, the output. And now that we have this value, now the second equation only has one unknown because we can plug this 4.33 into it. So 15 cosine 30 negative 0.5 plus sine 30 negative 4.33 equals y5 prime. And y5 prime then works out to be negative 8.66 inches per radian. And again, all of these prime terms are the kinematic coefficients. They're a ratio of output to input. And this is useful when input can change. So you can plug in any input value you want. So if you have a motor that has 3 different speed settings, you can just plug in rapid fire all 3 of your speed settings and find the 3 possible velocities that your output would be at. In this case, the speed is -5 radians per second, which gives us V5 43.3 inches per second. And so if you want a refresher on this complex algebra loop closure method in a more standard application where you're doing time derivatives, that'll be the video up on the screen here for some extra practice.